Welcome. Hello. I think we'll get started. We may have a few people trickling in, but I thought we would get going because I know you're all excited to hear from Erika. So hello. Welcome to another After Dark. My name is Amanda Fries. I'm the Senior Program Developer on the Public Programs team, and I'm really excited to welcome you all to After Dark from the ground up. This is in celebration of the ground, all of the life within it and that comes from it. So one of the things that we were running tonight was our pairing series. Did anybody get to check out Pairings Corn? A couple people, wonderful. This was one of our food science events that's been really popular for members, and so got to taste some tasty corn-based recipes and then learn about the science of corn too. We have been so thrilled to work with Point Blue Conservation Science, who is our program partner who brought most of the activities that we featured tonight. They have over 160 scientists working to reduce the impacts of climate change, habitat loss, and other environmental threats while developing nature-based solutions to benefit both wildlife and people. And they do this through both research and education and outreach. They partner with land and water managers, fishermen, ranchers, farmers, cities, counties, and more to improve the health of our planet. But beyond all of that, they're also just awesome. They're like wonderful people. So if you haven't had a chance to talk to them, you'll hear from Erika Foster tonight, who is speaking on behalf of Point Blue. But there's also multiple soil scientists and folks representing Point Blue down in galleries 2 and 4, where they've got painting with pigments that are derived from soil, tests that come straight from the field that you can use to learn more about soil. We are collaborating with our Living Systems lab here at the Exploratorium to learn more about the microbes that are present in compost and the fact that it's so alive. So if you didn't already make your way down to those 2 galleries down towards the other end of the museum after this talk, I highly recommend that you do so. And for our talk tonight, it'll be about 20 minutes or so long, and we'll have some time for Q&A at the end. I want to thank our AV team, as always, for making the talk possible. Thank you, AV. And then I'm really excited now to introduce you to our speaker for the evening. So our speaker tonight is Dr. Erika Foster, Director of Soil Research and Conservation at Point Blue. Erika earned her PhD in ecology in soil and crop sciences at Colorado State University at Fort Collins. Erika has worked on domestic and international projects related in part to soil carbon sequestration and microbial nutrient cycling to adapt conventional systems to drought and many other things. You'll hear more from her about her work. And she's also dedicated to environmental field education, having taught undergraduate courses for the Wild Rockies Field Institute and climate change and natural history courses for No Barriers Youth in Colorado, Gastineau Guiding in Alaska, and Tyrone Creek State Park in Oregon. And so tonight she's going to tell us about this project from Point Blue where they are mapping the carbon that is in soil all across California and the impacts that this work has had. So welcome, Erika. Thank you so much.
Amazing. Thank you, Amanda. And a big thank you from the team at Point Blue for attending tonight and to the Exploratorium for hosting from the ground up. I think this is a really unique After Dark, and I'm just really excited to share the below ground world with you. And I want to start tonight with a story that will take us down to the Amazon rainforest. And we are going on a hike, and it's at night, and there is a single track trail. Our local guide is in front of us, and in this situation, I was actually the responsible party for wrangling a group of high school students behind the local guide. So as we're hiking through the jungle, the sun has set maybe an hour or 2 ago, and I'm thinking in my mind about all of the things that could be potential hazards for these high school students: jaguar, anaconda, bullet ants, fire ants, poison dart frogs, and here we are with our tiny little flashlights. And as you scan out into the woods, you can see these tiny little trees, and then your light just disappears. There's nothing. It's completely black. So we get in about 10 minutes, and the guide says, "All right, everyone, I want you to first look up and then turn off your flashlights." And the instructor brain in me says, this does not sound like a good idea. However, we listened. They were fabulous guides, so we went ahead, we looked up, and we turned off our flashlights. And above us, you could see through the tree canopy in little patches all of the thousands of stars that were above us. And then the guide told us to look down at our feet. And when we looked down, it was as if the stars had just fallen out of the sky. The soil was covered in bioluminescent fungi in this massive network that just stretched out in all directions. And so I think this was a really amazing example of how if you just look at things a little bit differently, if we actually turn off the light in this scenario, we'll see this whole network beneath our feet that we couldn't otherwise observe. And so tonight we'll talk about how we can start to think about that underground network and these communities and ecosystems that are all in the soil. And just as an example, this is from a really incredible organization, this map, the Society for the Protection of Underground Networks. And this is a map of ectomycorrhizal fungi in California. So you can see we not only have these networks abroad, but really incredible biodiversity hotspots here at home as well. And so tonight, what we're going to do is think about how we can visualize some of these below ground dynamics. And we'll talk about how soil biota connect to soil carbon. And this journey will take us from global context into these little microscopic interactions. And that is why I love soil science, because it spans all of these scales. So we'll start off with a really quick introduction to how Point Blue does our science. We are aiming to conserve birds, other wildlife, and ecosystems through science partnership and outreach. And today our headquarters are in Petaluma, and they're situated on the unceded lands that are stewarded by Southern Pomo and Coast Miwok people, whose relationship with the land and the soils since time immemorial has allowed the development of ecosystems that we see today. And as this continued relationship carries into the future, we continue to partner and learn from Indigenous stewards and encourage others to do the same. So we got our start as an organization in 1965 as Point Reyes Bird Observatory. And to this day, after 60 years, we are still collecting bird data out at the Palomarin Field Station. That is open to visitors if you ever would like to go and check that out. So then our organization started a working lands group focused on agricultural lands, ranches, primarily and croplands. And then in 2020, we started our soil conservation program, and that is the team that's here tonight. Greg Richardson did a lot of organizing and is currently with the microscopes, so I encourage you to go check that out later. And Sophie Noda is also doing some of the texture tests along with Chloe Latt. So our research program is focused on determining the effective healthy soils management for resilient natural and working landscapes. And our key project areas include habitat and grazing management impacts, resilient restoration approaches with grasslands specifically, food sovereignty using prescribed and cultural fire, mapping below ground biodiversity, and agricultural conservation, which is synonymous in many ways with regenerative agricultural practices. And this is never done alone. As you just saw a preview, we have many partners that are with us along this journey. And so for tonight, I want to focus on how you too can start loving soils as alive ecosystems as much as I do, to meet and greet some soil biota, determine how those biota rely and relate to soil organic carbon, and then finally we'll get into our mapping, thinking about the global context of soil carbon, and then dive into state maps and regional patterns and mysteries, and then finally, how to become a soil conservationist in your own backyard or community. So we'll start with the Science and Soils 101 to introduce you to the diverse world beneath our feet. So soils provide many different benefits for human society, ultimately serving as the foundation for civilization and buildings, food and fiber, water storage and filtration, climate regulation, and they are just beautiful. If you ever stop to notice, soils are super diverse. And we encourage you to check out those soil pigments and just find out a little more about how diverse those colors and chemistries can be. It also provides habitat for over 59% of global biodiversity. And yes, this does include plants. 85% of plant species are based in soil, 90% of fungi, and then about 84% of Isoptera. And there's so much more living below ground, I would be remiss not to introduce the rest of the players. So we'll dive, these organisms drive the global biogeochemical cycles from the microbial scale all the way to the megafauna. And the soil really provides the shelter, including food, water, air, space, and structure. And importantly, all of this is really connected to the soil organic matter. It creates all of these amazing networks and different aggregates or groups of soil particles, and so it really holds the water and nutrients and serves as a food source for these organisms. And broadly, higher soil organic matter and the carbon that's within it links to more biologic cycling and makes this a basic indicator of healthy soils. And my favorite soil critter is the tardigrade, which is extremely hardy and can stay desiccated for decades and awaiting the perfect time to wake up again into its soil home. So these organisms, again, many of them are cycling that organic matter and the carbon within. So let's take a look at the global carbon cycle to really put this into context. So we all know photosynthesis is pulling carbon dioxide out of the atmosphere. Vegetation contains up to 650 gigatons of carbon after a plant senesces or through sloughing off of roots and direct exudates into the soil to attract microbes. That plant is actually releasing carbon below ground. And that root pathway is often called the liquid carbon pathway. So that's how soil organic carbon forms, and we have this gigantic pool in the soil, up to 2,400 gigatons of carbon, which is 3 times the amount in the plants and the atmosphere. So this is a really important pool to protect and to build, and we have many different practices that allow us to do that. So that includes different conservation or restoration practices and regenerative agriculture. And if you're kind of scratching your head about what exactly a gigaton of carbon is, it's about 3,000 Empire State Buildings in weight, or 2 Californias of corn, or 611 coal-fired power plants in their annual emissions. So over time, we have lost about 117 gigatons, or petagrams is another term, to the atmosphere through human land use change and agricultural practices. So that's about 36 parts per million of CO2 that we've lost into the atmosphere. So now the question is, how do we protect that carbon and how do we potentially build that carbon back into the soil? And so we have many different management strategies that we can use: direct seeding, transplanting grasses, forbs, shrubs, and trees. Really anything that boosts plant productivity will have an impact likely on soil organic carbon. We also can use mechanisms that slow water on the landscape, like beaver dam analogs. And in California, we know that water is really critical to productivity. So just slowing that flow across the landscape can have a really big impact on plants and therefore soil carbon as well. And even grazing, we've been researching recently, can have an impact on soil carbon. And although it could be smaller than some of these other practices, we're starting to find out how that could apply across the state of California. So as a land manager, you have all of these options. Each of these takes time and energy. So which one of these practices do you choose? Well, it depends on what your target is. There could be multiple benefits of soil carbon. We've talked about those ecosystem services. So if we're trying to target one thing, soil carbon or plant production can be a really good indicator of overall health and productivity of the site. And so now we're using carbon to launch this National Agricultural Conservation Monitoring Program, and we track changes due to the conservation practice in above ground and below ground carbon as well. And this was a really incredible project because it brought together all of these technical experts and practitioner advisors, so farmers and ranchers directly working on these protocols to build this scientific basis that allows us to standardize the data set in a very flexible and accessible manner. And so this effort is expanding. We now have data from 6 different states, and we're looking to continue to expand this program. This program also builds on 10 years of data that we had specifically from our rangeland monitoring network. And this network, again, focuses on the multiple benefits. And here we directly measure plant communities, bird communities, as well as soil metrics of carbon and compaction. And so today what we'll present and map is some of this data that's over a decade old to try and tease out patterns of where conservation practices could be most impactful. So we'll focus again on rangelands across the state. And here we're using digital soil mapping across the extent of rangelands that you can see pictured there. And we're attempting to predict and assess carbon changes and see where those differences in prediction versus our direct measurements lie. And then that will indicate where more storage potential might occur. And so we input multiple data layers: land cover, elevation, climate, vegetation, and soils. And we can build maps from 0 to 10 centimeters is what's represented here, or about 6 inches. And we predicted that stocks of soil organic carbon can range from about 6 to 60 megagrams per hectare. And to put that in context, that's about 2 football fields, or the size of Pier 15 in a hectare. And about 1 tall tree or 1 year of driving is a megagram of carbon. So it's as if you take Pier 15 to get to like the average, you could take Pier 15 and plant 5 to 15 tall oak trees. And that would be the equivalent just in the top 6 inches across this area. We've observed really high correlations between our predictions and the measured values, and a lot of those are based on vegetation indices. And we find that our largest stocks are along the coast, and so you can see towards Santa Barbara County, and also just below the city, we have really high carbon stocks at the surface. Our lowest carbon stocks are in areas with extreme seasonal changes and also water deficits, as we would expect. So overall, if we compare our expected modeled results to what we actually measured, these are areas where we estimate there could be a deficit. So the areas in red were areas that we would want to target some of these conservation practices. So overall, the California rangelands are seeing an annual change, an annual loss of carbon. And these are often in carbon-rich soils because they're more susceptible to losses. There's more carbon to lose there. And we know that climate change likely drives these losses based off of the indices in our model. And so this map can help to guide incentives of conservation practices along these high loss areas, like the San Joaquin, Alameda counties, and Stanislaus, and then down in Santa Barbara as well. And so this map, as we continue to tease out this analysis, can help us to meet state climate targets for natural and working lands. And again, regardless of whether or not we're actually building or maintaining carbon in these sites, it is a really important pool of carbon at about 430 million megagrams of carbon down to 40 centimeters. So we want to make sure that we have ways to build and protect and also slow carbon losses. And what's really important here is to consider the context of all of these sites. We have different producer communities and different practices that will be more or less accessible. And so I want to bring us to an example of a regional partnership down at Tomcat Ranch in Pescadero. And this is a mystery of soil carbon losses. Down at Tomcat, we have this incredible team of land stewards and producer assistants and really incredible scientists who work down at the ranch who have these really amazing ecological questions and are very aware of how management could impact the ecology at the site. And so every 3 years, we go out and we sample soils in the Rangeland Monitoring Network, and we produce these reports. And we have found that we see this slight continual decrease in soil carbon at the site. So here on this map, every circle represents both the surface sample from 0 to 10 in the small dot, and the larger dot is 10 to 40 centimeters. And the orange are areas that are declining. And I actually looked at this as an example of how variable soil carbon can be across a landscape. And not only do we have variability in how much carbon is at each one of these dots, but also how the change is occurring as well. And we looked into soil microbial dynamics, and these blue spots that are gaining carbon also have the highest soil biodiversity. So we've got some clues in here. But I think this is a great showcase of ecological dynamics and variability. There's a wider context here of California grassland transition from perennial grasses to annual grasses, which causes a loss of carbon. There's also a transition of climate and increased drought. And we also have this loss of the influence of the mist at the site. And so that also influences plant productivity in this coastal ecosystem. So knowing your context is extremely important. Now, so that brings us to one of our smaller scales of the evening, which is soil science in your own backyard or your own community. And we actually have a few of these printed out at the tables in Gallery 4 on the other end. So if you're interested in taking something home, you're welcome to one of those. And we really want you to think about some of these patterns that you're seeing across the globe and across California and regionally, and then bring those into your own backyard. And that could be really simple through different observations. And so I want to highlight a few kind of unique features of these different senses you can use and observations you can make. And one of my favorites is looking for legumes. So if you have beans planted, if you have any lupin around, perhaps even on a hike, it's really fun to dig for nodules. And these are little tiny balls on the roots that house Rhizobium and Frankia bacteria that fix nitrogen directly. And if those are functioning well, they are pink, like a nice rare steak. And so you can assess the health of those nodules. And we can talk more about soil enzymes after the fact. Soils also, if you're digging up a plant and looking at roots, you can also check to see if there are soil aggregates attached to the root. And so that could be a sign that the soil has good structure, that the roots are part of that liquid carbon pathway in feeding the microbes. And so that's a really good indicator of soil health as well. Water features that support life are super important. And thinking about, even just little interactions that support birds, for example, can help to benefit the ecosystem. And then again, wildlife overall, I like to think about insects as wildlife too. Sometimes those critters are forgotten. So dragonflies as apex predators, and thinking about creating bee houses and things of that sort can be really important. And then also smell. So this can be a little tricky with soils, but here we do have some great winter rains, and there's this phenomenon of petrichor, which is a scent, and I'm sure many of you have smelled it after a rain, and that comes from the geosmin that's produced from Streptomyces bacteria in the soil. And so that is something that you can notice, and it could be an indicator of healthy living soil. You can listen for non-human sounds, and then also feel if the soil is crumbly or spongy beneath your feet. And if you want to get really nerdy, you can also map your own soil with the USDA Web Soil Survey. I took a look at the Presidio for us tonight, and so if you want to be able to go and tell your friends that you actually have like an RGU stall in your neighborhood, then this is the place to go. And that can actually tell you quite a bit when you break it down. This is a clayey, humid soil that was a grassland at some point. And overall, you can keep in mind practices of soil health principles to cover the soil and keep natural mulch or plants. Try not to disturb the soil as much as possible. Keep living roots year-round. Promote biodiversity. And again, to remember your context. And if you'd like some more practice with any of these, you can go on and check out the activities. And this will help you to continue your illumination of soil science for the evening and beyond. So I hope tonight we have unearthed different ways to start to see the world beneath your feet. We've met a diversity of biota that are cycling carbon. We've connected those biota through the plant photosynthesis and the liquid carbon pathway as how soil organic carbon forms. And then we've mapped soil carbon, putting it into the global context and storing those petagrams of carbon and gigatons. Then we went into the statewide climate change impacts and solutions through regenerative and conservation practices and monitoring. And then finally brought it into the context of your own backyard. So please continue to learn to find new ways to dig into this new world and get your hands dirty. And as we learned from the story at the start of our time together here tonight, from the jungle fungal story, I suppose, you might just take a little change or make a little change in how you observe your environment, and that can really open up whole worlds beneath your feet. So in that way, we can all start thinking and learning and exploring from the ground up. Thank you.
Erika, thank you so much. So before we jump into Q&A, I want to give you all a chance to reflect with your neighbors about something you saw in Erika's talk. So let's take 30 seconds, come up with a question or a comment that you have about Erika's talk, and then we'll dive in. I mean it. Talk to your neighbors. It's so true. Like there is a universe down there too, and the same sort of scale.
Yeah. I slowed down a little bit. I realized that I was maybe blowing through things, and then at the end I was like, oh yeah, I think my timer was up there. So.
We're right on time.
Okay.
All right. What sorts of questions or comments do we have for Erika? Yes, great.
Oh gosh. Yeah, my question was about challenges in soil remediation in urban spaces versus grasslands. Just given that we have a lot of variables with our presence, our industries, and how we function there. Like, what are some challenges and methods or solutions that have been successful?
Yeah, this is a great question, especially given that we're on urban soil right now across the pier. So I would say there's a couple different methods that come to mind. The first that can be really important is bioremediation. And so that's planting typically plants. I know that sunflowers are really good accumulators of heavy metals. And so that could be a good example to try and extract some of those metals. And then you need to, of course, dispose of the plant biomass in a safe way afterwards. And then in some contexts, if you don't have bioremediation as an option, you can essentially scrape soils as well. So there could be examples where you have to remove topsoil, for example, if you wanted to plant a garden or a farm at some site. And so that could be a really extreme example. When I think about gardening on urban soils, if you're not able to test your soil specifically, then you can use a method that's lasagna gardening. And so you just don't disturb the soil at all, and you actually just layer cardboard and then a layer of alfalfa or hay and then compost and maybe some topsoil from elsewhere, and you just plant directly into that. Yeah, thanks.
Other questions? Yeah.
Erika, thanks for your talk. And I just loved your story about being down in the Amazon. And I'm wondering if there's any kind of bioluminescence like you talked about down there, anywhere in the Bay Area. And if it is, where can we go and see it? And if we don't have it anywhere nearby, is there something, was it here at some point? Is there something that can be done that can help to bring it back?
This is a question that I also want to know the answer to. We had a conversation with the SPUN organization recently about some of their maps, and we're just getting to think about how we can layer those ectomycorrhizal maps on top of our soil carbon maps and look at biodiversity. So I will get back to you on that answer. And maybe we could do a hike to go and find some. And then I think it's just, I've seen bioluminescence in the bay. And so I think that it is a feature that evolved potentially to attract insects, to help to promote sporulation and spread spores of the fungi. And so I would anticipate with the biodiversity of California soils and fungi as well that we might just have some here.
Time to go on a bunch of night hikes.
Hi, thank you for your talk. I was wondering, in the example of Tomcat Ranch or any other rangelands, you've been seeing increased or decreased biodiversity in the soil. Have you been able to tell why that's happening, or able to make any recommendations on how to improve it?
So at Tomcat, we have, this is a great example, we have a single time point for soil biodiversity. And so in order to see if it's increasing or decreasing, we need to go back and remeasure, which is always challenging because it's so diverse also that you want to make sure you capture as much as possible. And so we are doing work now with the California Institute for Biodiversity to try and answer some of those questions, specifically on ag lands. And so right now we're doing kind of a first round of sampling for that also. And it's very different than sampling for soil carbon, where you have to be very careful about keeping the samples separate and mapping variability. For biodiversity sampling, we just go out and we take as many samples as possible. We can go and find the coolest spot at the site and sample there, which we never want to do. We always try and randomize for soil carbon. So we're collecting as many species and taxa as possible in those samples across specific sites, and then geolocating each of those so we can go back and start to answer that question. And so the Institute for Biodiversity is really leading that work, and it's essentially a citizen science project. And so they're really kicking it off now and have protocols that we've also helped develop along the way. And so we hope to have answers to that question too. And just mapping biodiversity across California alone is going to be the first step, and then changes will be the second. Yep.
We have time for a couple more questions. I'll walk around. Yeah. And one back. Okay, I'll come back to you. Oh, okay. Great, thanks.
And as the mic is moving, I'll say, in order to protect biodiversity, those principles of soil health are going to be really important. So keeping the soil covered, keeping a living root in the ground, and maintaining above ground biodiversity would help to protect below ground biodiversity.
Does root depth also play a part into it?
Definitely. So, and that's a great link into that shift from the annual grasslands or the perennial grasslands in California that had very, very deep-rooted dynamics to annual grasses, and why we're seeing those soil organic carbon losses in many places across the state. So rooting depth allows that liquid carbon to go into areas where there are fewer microbes, and so the carbon will stick around a bit longer at those deeper depths in the soil.
I'll give it to you.
What's biota? Did I miss that?
So any kind of soil organism. So animals. And we have what we like to call, so there's the microorganisms, so bacteria and fungi and archaea. And then we have we said microorganisms. Then we have mesoorganisms, which are slightly larger, which could be the tardigrades. I'm getting a little confused. The mesofauna would be something that you can almost start to see with your naked eye. So like springtails would be an example. And then we have macrofauna, like worms and spiders and slugs. And then what we consider megafauna, which would be burrowing owls or gophers and critters of that side.
Any last questions? All right, let's thank Erika one more time. Thank you, Erika.